In this video, we introduce the idea of the derivative of a function at a point x equals a. So why don't you pause, copy down this panel, and then press play. We're in section 3.1 of the text, Intro to the Derivative, and we've done some of the groundwork for this earlier in the course. So consider this graph of f, which is kind of parabolic. Earlier, we calculated the average rate of change of f between two x values, a and b. And if you recall, what we did was we plotted the point a f of a and b f of b, and then we connected those 2 points by a line that we called a secant line. So secant line means it touches the graph twice. And we calculated the slope of that secant line. And this was the average rate of change of f between the two x values. So we used the second y value minus the first y value. So f of b minus f of a, that's the rise, divided by the run, which is b minus a. So that was a rise over run computation, and it gave us the average rate of change, okay? Now, our goal is going to be to figure out the slope of this tangent line to the graph of f at x equals a. And we kind of had some problems related to this earlier as well. So the slope of the tangent line, we call that the instantaneous rate of change of the function at x equals a. Excuse me. Okay, so we will call this slope of the tangent line the derivative of f at x equals a. All right, so the derivative of f at x equals a, our notation, how we denote it, will be f apostrophe parentheses a, and we'll say it f prime of a instead of f apostrophe. We'll say f prime of a. All right, but the question is, how do we calculate the slope of this tangent line? Slope of the secant line, I mean, that's easy. It's rise over run between 2 points. How can we adopt that definition to get the slope of a tangent line upon which we only have 1 point on the graph of our function f that is on the tangent line? All right. So again, why don't you pause, copy this stuff down, and then I'm going to fill some of this stuff in, okay? All right, well, let's sort of recall how we worked about doing this in an earlier assignment. There's my graph of f again. I'm trying to estimate or approximate the slope of that tangent line. So what I would do is I grab a point near a, and let me call that a plus h1. And I'd plot that point on the graph. So that's a plus h1 comma f of a plus h1. Connect those 2 points with a line, and I can calculate the slope of that line, that secant line, as the change in the y values. So f of a plus h1 minus f of a all over a plus h1 minus a. Now, the only thing I'm going to do is I note that the a minus the a knocks itself out, and I just have an h1 in my denominator, okay? All right, and then I can say, well, hey, the slope of this secant line, it's close to the slope of the tangent line. But I could probably do better. And I could probably do better by picking a smaller value for h than I did for my first h, okay? So maybe I'm going to pick an h2 that's less than h1 and plot a plus h2. This would be a point that's closer to a comma f of a. Should have wrote that down there too. So I could pick a second point on my graph closer to my initial point. Let me call that point a plus h2, f of a plus h2. I can connect those two with a secant line and then do my slope calculation again. So f of a plus h2 minus f of a all over a plus h2 minus a. And again, the a's cancel each other out, so the denominator simplifies to just h2. All right, well, this gives me an idea of how to continue that process. I could say to myself, well, let's keep picking h's smaller and smaller and smaller and just go from a to a plus these small h's. So I could try and say, well, I'm just going to grab this other point, a plus h, small h, and then f of a plus h. And do my little secant line thing. And the change in y would be f of a plus h minus f of a. And then a plus h minus a would again just leave me with an h because the a's would knock each other out. Now, I'd like to let h go really, really, really small, and we now have a mechanism of doing that. I'm simply going to tack on a limit. And I'm going to let h get really, really small. I'm going to let h go to 0. And that is going to be the slope of our tangent line. So it's the limit of the slopes of secant lines as the second point gets closer and closer to the first point. And we get that second point closer and closer to the first point by letting the h go to 0. All right. So there is the slope of the tangent line, which we also know is the derivative at a. So just using that notation we introduced. All right, now this is not terribly important, but there's an alternate way of writing a derivative or the instantaneous rate of change, the derivative as a limit. So down here, I could have said, look, I've got my point that I'm interested in, a comma f of a. And what I'm going to do is I'm going to grab an x value later on, and let me just say that's an x comma f of x, and I could calculate the slope of the secant line between those 2 points, rise over run, okay? So I'm using an x instead of an a plus h. Great. Well, and then I can say, well, I'd like to do this secant line as x gets closer and closer to a. So I'm going to keep this secant line slope just exactly like it was in the line above, but I'm going to I want x to get really, really close to a. So I'm going to take a limit again. I'm going to take the limit as my x value gets closer and closer to this spot a that I'm actually interested in. So this is also a way of calculating the derivative of f at a, or calculating the instantaneous rate of change of f at a, or calculating the slope of the tangent line to the graph of f at x equals a, all right? So there's a lot of different ways to say what I'm doing. There's a couple of different limits I can use to compute this object. I hope to clarify that on the next panel. All right. So again, I would pause, copy this down, then press play. All right, so what we are trying to do in those last 2 panels is figure out a way of calculating the instantaneous rate of change of f at a given x value, x equals a. This is equivalent to calculating the slope of the line that's tangent to the graph of f at x equals a. And tangent means the line just barely glances off of the graph of f and touches it in exactly 1 point, okay? Another way of thinking about the tangent line is if you've got a curved graph and you pick a spot, if you zoom in on that spot really, really far, that curved function will start to look like a line if you zoom in far enough. That line's the tangent line, okay? So you could also think of the slope of the tangent line as the slope of the function itself at x equals a. We'll expand on that later in the course. All right. So the instantaneous rate of change of f at x equals a is the slope of the line tangent to the graph of f at x equals a. We calculate it either via this limit, the limit is h approaches 0 of f of a plus h minus f of a over h, or we calculate it via this limit. The limit is x approaches a of f of x minus f of a all over x minus a. And both of those are basically just secant line slopes where the second point is getting closer to the first point. So the secant line is getting closer to the tangent line. We denote this instantaneous rate of change, this slope, as f prime of a, and we say it is the derivative of f at x equals a, and we would say this as f prime of a. All right, I'm going to do 2 examples of actually calculating a derivative. Here's the first one. I've got a nice happy polynomial, negative 2x squared plus 3x minus 5. I'm going to calculate the derivative at a given x value, x equals 3. So in this case, my a is being played by the number 3. And I'm going to use this first limit that we created, okay? All right, so let me set this up. F prime of 3 is what I'm calculating. I'm going to take the limit as h approaches 0. Well, according to this, I'm going to do f of, whoops a daisy, f of 3 plus h, there's my a plus h, minus f of 3 all over h, okay? So all I did was I took this limit in number 2 here and replaced a with h. Sorry, I replaced a with 3. All right, now I'm going to plug 3 plus h in for x in my function. All right, so there's my limit because I haven't taken it yet, so I continue to copy it down, obviously. And every time I see an x, I'm going to replace it with 3 plus h. So I've got a -2, an x squared, so that x is now a 3 plus h, plus 3 times an x, 3 times an x, which is now a 3 plus h, minus 5. So all that was f of 3 plus h. Okay, now I need to subtract f of 3. I'm going to put some parentheses to make sure that subtraction sign applies to everything. So now I'm going to take 3 and plug it in for every x. So I've got -2 times 3 squared plus a 3 times an x, which is replaced by a 3, and minus a 5. So I've replaced each of my x's with a 3, and then I'm dividing all this by h. Okay, all right, so it's a bit of a mess. Now, the name of the game is, I can't do direct substitution because it would give me a 0 in the denominator. But what I'm going to do is I'm going to destroy all the parentheses in the numerator, simplify it, and hopefully I'll be able to cancel that problematic h out of the denominator and then do direct sub and get my answer. Okay. All right. So destroying all parentheses. Let's go down here. Limit h approaches 0. First off, let me take 3 plus h and multiply it by 3 plus h. That's going to give me a 9 plus a 3h plus a 3h plus an h squared. Okay. And then I'm going to run a -2 through it. Okay. And I'm going to write the answer down on my main line. So the -2 times the 9 is going to give me a -18. -2 times, well, that's a 6h. -2 times 6h is going to give me a -12h. And the -2 times the h squared is going to give me a -2h squared. Okay. All right, so that took care of the -2 times 3 plus h quantity squared. Run the 3 through the 3 plus h, and I think I get a +9 and a +3h. I've got a -5. And then let's see, in here, I've got -2 times 3 squared. 3 squared is a 9, so that's a -18. That's a 9, and that's a -5. Okay, so if I run the minus sign through, I think I get minus a -18, so I get plus 18. I think I get minus the 9, and I think I get minus the -5, which is a +5. Okay, so you should check my arithmetic on this, but I think that's how it's coming out. And then downstairs, I get an h. All right, well, let me take the red pen of cancellation death and see what dies up in the numerator. I've got a -18, which is counteracted by the +18. I've got a +9, which is counteracted by a -9. And I've got a -5, which is counteracted by a +5. Okay, and I think I've got a little bit more that I can do, but I think those are the numbers that kill each other out. So let me just start to copy stuff over. Limit h approaches 0. I've got -12 of the h's and +3 of the h's. So I think all told, I have -9 of the h's. And then I've got a -2h squared. And then I've got that h in the denominator. Okay. All right, so it's tidied up a lot. And I note that the numerator, both terms have an h in it. So I could factor that h out in front. So if I come down here, I've got a limit h approaches 0. I'm going to try and factor an h out in front of my numerator. So if I drag an h out of a -9h, I'm left with a -9. If I drag an h out of a -2h squared, I'm left with a -2h. And then I have that h in the denominator. All right. And factoring that h out in front of the numerator now allows me to cancel with that problematic h in the denominator. And that h in the denominator was what was preventing me from doing direct substitution. It's now gone. So I'm going to do direct substitution. I'm going to replace h with 0. And let's see, I think I have a -9 minus a 2 times 0, which is just -9 minus 0, so just -9. So the instantaneous rate of change of this function at x equals 3 is -9. I could also say the derivative f prime of 3 is equal to -9. Okay. All right, so I just had to wade through an ocean of algebra, but eventually things canceled nicely. All right, let me do one more example. Stay tuned. Start copying that down. All right, so now, slightly different question. I need to determine the equation of the line tangent to the graph of this function g at x equals 2. Okay. So I don't just want the slope of the tangent line, I want the whole equation of the tangent line. And I'll just remind you of a few things. To get the equation of a line, I need two things. Number one, I need a point on the line. Okay. All right. And I don't know what this graph looks like, but let's just say it looks like that. And there's x equals 2. The tangent line touches the graph at 2 and then just sort of glances off. Missed it. I didn't, just bigger dot. Kind of glances off there. But I know the tangent line touches the graph at 2. So 2 comma g of 2 is on the graph of g and the tangent line hits it. So the point on the line I'm going to use, and we'll always use for tangent line questions, is the x value they provided and then the output of the function at that x value. So it's the point on the graph at x equals 2. Okay. All right, and I might as well calculate that now and be done with it. So let's see, 2, g of 2 would be the square root of 2 times 2 plus 1. Square root of 4 is a 2 plus 1 is a 3. So there's the point on the line. Okay. All right. And then the second thing I need for the equation of the line is the slope of the line. Now I'm after the slope of the tangent line, and I know that's the instantaneous rate of change or the derivative of the function at 2. So I'm after my slope is going to be the derivative of my function at 2. Okay, so I'm going to do a fair bit of work to calculate this derivative using our limit, and then I'm going to have my slope and a point on the line, and I'll put together the equation of the line. All right, so over here, let's do g prime of 2. And I'm going to use that limit involving h. All right, my a value is 2, so I'm going to do g of 2 plus h minus g of 2 all over h. Okay, so there is my limit definition of my derivative with g instead of f, and a is being played by the number 2. Okay, so now I'm going to get my function moving on here. So I'm going to take my function g, and every x is going to get replaced by a 2 plus h. So here's my function g. So starts with the square root of 2 times the x, and that x is going to get replaced by a 2 plus h. And then I have a and a square root plus 1. So that's g of 2 plus h. And then I need to subtract g of 2. And I'm going to do it again just for funsies. I'm going to put the g of 2 in parentheses, replace x with a 2. So it's going to be the square root of 2 times 2 plus 1 all over h. Now, I already calculated g of 2 up here and I got 3. So let me just substitute that in and tidy things up a little bit. Okay. All right. So back down to here. Limit h approaches 0. I don't think I'm going to do anything with this first part of the limit fraction. I'm going to have a square root of 2 plus h. Whoops, plus 1. There's a plus 1, yeah. All right, and that's minus a 3, right? Yeah, that was the 3 we had before. Minus 3 over h. All right, and I was hoping that I could figure out how to cancel this h in the denominator because that's what's stopping direct substitution. But it's not looking good, but let's just go a step further. Limit h approaches 0. I've got my square root of 2 times 2 plus h. Plus 1 minus 3 is minus a 2. Okay. All right, well, I don't see anything canceling. I don't see any algebra I can do to simplify this, but I do see a square root being added or subtracted with something else. So I'm going to do my conjugate trick, okay? So I'm going to take the conjugate of the numerator. So that's going to be the exact same square root, not changing anything there. the exact same number at the end, and instead of a minus sign, the only difference will be a plus sign. And whatever I do to the top, I must do the exact same thing. Oops, daisy, the exact same thing to 2 plus h plus 2, multiply the exact same thing to the denominator, okay? All right, now, if you remember, I'm going to go FOIL out the numerator, but leave the denominator alone. So the object times its conjugate is going to tidy up nicely. The other part of the fraction is not going to tidy up at all, so I'll just leave it be. So back down to here. Let me write down my denominator first. So I'm not doing anything with that. I had an h. I had a square root of 2 times 2 plus h. My conjugate was adding 2. Okay, so there it was. So there's the denominator. I just mushed them together, didn't touch anything. Now, numerator, I'm going to FOIL it out. The square root times itself, I just get what's underneath the square root. Like the square root of u times the square root of u is a u, right? So the square root of 2 times 2 plus h times itself is just 2 times 2 plus h. So that's the first multiplied together. Then with the conjugate, we always know that the outers and the inners are going to knock each other out. Because look, I've got positive 2 times the square root, and then I've got negative 2 times the square root. So those two cancel each other out. I'm not even going to write them down. And then I have negative 2 times positive 2 for the last of the FOILings. So negative 2 times positive 2 is a negative 4. Okay. All right. So the numerator's gotten a lot cleaner. Let's continue to clean up the numerator, destroy all the parentheses like I did with that polynomial example. H approaches 0. If I run the 2 through, I get a 4 plus 2h minus 4 all over h times that conjugate to 2 plus h plus 2. Okay. All right. And look, the 4s knock each other out. So I've got the limit as h approaches 0 of 2 times h over h times that conjugate mess plus 2. All right. But we have some joy. I have an h being held by multiplication on top and an h being held by multiplication downstairs. So those two cancel each other out. And I've killed off the problem in the denominator, so I can now try direct substitution. So now I do direct sub. I'm replacing every h with a 0. Well, up top, there's just a 2 that survived. There's no h. Downstairs, that h is gone, so the need of the parentheses is gone. So let me just write this as 2 times 2 plus, the h gets replaced with a 0 by direct substitution, plus 2. And let's see, that's a 2 on top. 2 times 2 is a 4, so the square root of 4 is a 2. So I think I have 2 over 4, which is 1/2. Okay. So my derivative is equal to 1/2. And if you recall, my derivative is the slope of my tangent line. All right. So here's what I've got. I've got point on tangent line was 2, 3, and I now have slope of tangent line is 1/2. The derivative is the slope of your tangent line. So let's just come over here and finish the equation of the tangent line. So I'm going to do y minus my y value equals my slope times x minus my x value. So that's the point slope form. You have a point on the line and the slope. Y minus your y value equals m times x minus your x value. Okay. So there's the equation of the tangent line. If you want it in mx plus b form, fine, I can do that. A few more steps of algebra, run the 1/2 through. I get a 1/2 times x. A 1/2 times a -2 is a -1. And I can add 3 to both sides. And I'd also get y equals a 1/2 x. -1 plus 3 is plus 2. So there's the equation of the tangent line. Either of these is the equation of the tangent line. Okay. So the derivative is telling us the slope of the tangent line. we obtained a point on the tangent line, which is the point the tangent line shares with the actual graph of the function. And then we did our algebra work to get the equation of the line.